March 7, 1944. Somewhere over the Ruhr Valley, Germany, 23,000 feet. Lieutenant Robert Johnson's P-47 Thunderbolt shuddered as the first 20mm cannon rounds punched through the fuselage behind his seat. The metallic crack of impacts came so fast they merged into a single sustained roar, like hail on a tin roof, except this hail was travelling at 2,000 feet per second, and each piece could tear through aluminum like tissue paper. Johnson's instrument panel exploded in a shower of glass and sparks. The control stick jerked violently in his hands. Through his shattered canopy, he could see the Focke-Wulf 190 that had bounced him from above, its wings strobing with muzzle flashes as the German pilot held down the trigger, pouring round after round into the American fighter. The math was simple. A Focke-Wulf carried 4 20mm cannons and 2 13mm machine guns. At maximum rate of fire, that meant roughly 120 rounds per minute entering Johnson's aircraft. He had been under fire for approximately 10 seconds. The P-47's massive radial engine coughed once, then continued running. Johnson pushed the throttle forward, feeling the Pratt & Whitney R2800 respond with 2,400 horsepower that had nothing to do with optimism and everything to do with 18 cylinders, arranged in 2 rows around a crankshaft that weighed more than most fighter aircraft engines entire. In a Luftwaffe operations room 200 miles away, intelligence officers were compiling reports that made no sense according to everything German fighter pilots had learned about aerial combat. American P-47 Thunderbolts were absorbing punishment that should have been catastrophically fatal, then flying home to land with damage that seemed incompatible with controlled flight. Some aircraft bore over 200 bullet holes. One had returned with 3 cylinders completely destroyed. Another had landed with hydraulic fluid streaming from dozens of punctures, yet the pilot had walked away without injury. The German assessment, written in precise technical language that barely concealed professional frustration, concluded that the P-47 represented something fundamentally different from previous American fighters. Not faster, not more maneuverable, but possessing survivability characteristics that violated conventional understanding of aircraft vulnerability. The morning briefing at Manston Airfield had begun at 05:30, recorded in the 56th Fighter Group operations log, with the bureaucratic precision that turned individual missions into statistical data. Colonel Hubert Semke, commanding officer whose tactical innovations would reshape fighter operations across the European theatre, stood before assembled pilots with reconnaissance photographs, spread across a wooden table that still bore coffee stains from the previous night's planning session. The target folders showed industrial complexes outside Essen, factories producing everything from ball bearings to artillery shells, defended by flak concentrations that could fill entire sections of sky with lethal fragments. Intelligence estimates indicated moderate German fighter presence, perhaps 40 to 60 Messerschmitt 109s and Focke-Wulf 190s scrambled from dispersed airfields across the Ruhr. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Weather reports noted scattered clouds at 15,000 feet, visibility good, winds from the west at 20 knots. Lieutenant Johnson sat among pilots receiving mission assignments, his logbook recording 18 previous combat sorties that had taught him the difference between training manual tactics and survival over occupied Europe. The P-47 Thunderbolt he would fly that morning carried serial number 4226471, nicknamed All Hell, a name that reflected less bravado than acknowledgement of what awaited beyond the English Channel. The aircraft log recorded previous battle damage, flak holes in the port wing, hydraulic line repairs, and canopy plexiglass replacement from a previous encounter with German fighters. Ground crews had loaded 850 caliber machine guns with 2,700 rounds total, plus a single 150-gallon drop tank for extended range over enemy territory. Semke's briefing emphasized formation discipline and mutual support during fighter sweeps ahead of bomber formations. German controllers monitored Allied radio frequencies, adjusting interceptor deployments based on communication patterns and approach vectors. Pilots received code words for navigation checkpoints and emergency procedures that everyone hoped would remain theoretical. The tactical reality was straightforward. P-47 would fly offensive patrols over German airspace, engaging Luftwaffe fighters wherever encountered to establish local air superiority before bomber streams arrived. The doctrine assumed that American fighters possessed advantages in firepower and durability that would prove decisive during sustained combat. Operations expected moderate losses, perhaps 2 aircraft from 36 dispatched. But mathematical probabilities and individual survival occupied different universes, and Johnson understood that statistics provided cold comfort when German cannon shells were entering your aircraft at closing speeds exceeding 600 miles per hour. Engine start procedures began at 06:45. The Pratt & Whitney radial cuffed blue exhaust smoke that dissipated in cold morning air, settling into the deep-throated rumble that distinguished P-47 from every other fighter in the European theatre. Radio checks confirmed interphone clarity. At 0700, the first aircraft lifted from the runway, followed by others at 32nd intervals as squadrons formed up over the English countryside before turning southeast toward occupied Europe. January through March 1944, Republic Aviation Corporation facilities, Farmingdale, New York. The factory floor stretched nearly half a mile, filled with P-47 Thunderbolts in various stages of assembly. Joining 8,000 employees, producing fighters at rates that had climbed from 40 aircraft per month in early 1943 to over 100 per month by the beginning of 1944. The transformation of Farmingdale from modest aircraft manufacturer to major wartime producer had required industrial mobilization on unprecedented scale. Republic had purchased farmland surrounding the original facility, constructing assembly buildings that covered over 1 million square feet. Railroad spurs delivered aluminum stock, steel forgings, and engine components from suppliers across the northeastern United States. The logistics of coordinating 15,000 individual parts per aircraft, sourced from over 300 subcontractors, required planning systems that resembled military operations more than traditional manufacturing. Factory ledgers recorded exacting specifications. Each P-47 required approximately 15,000 individual parts, assembled with tolerances measured in thousandths of an inch. Wing spars, manufactured from aluminium extrusions, had to meet stress tolerances that would determine whether the aircraft could withstand combat maneuvering loads exceeding 6 G-forces. Fuselage bulkheads required precise alignment to maintain structural integrity during high-speed flight, where aerodynamic pressures could exploit any weakness in assembly. The airframe weighed 5,000 pounds empty. Adding fuel and ammunition brought combat weight to nearly 14,000 pounds, making the Thunderbolt the heaviest single-engine fighter in operational service. Critics had questioned whether such a massive fighter could compete with lighter, more maneuverable opponents. But Alexander Kartveley's engineering calculations had demonstrated that structural strength and system redundancy would prove more valuable than pure performance optimization in sustained combat operations. American production capacity could replace combat losses faster than pilot training programs could generate experienced flyers, but each veteran pilot represented irreplaceable combat knowledge accumulated through survival over defended European airspace. The mathematical relationship between pilot experience and combat effectiveness meant that aircraft survivability directly influenced operational capability in ways that pure production numbers couldn't capture. A pilot who survived 10 missions in a durable aircraft became far more valuable than replacement pilot in a higher performance fighter that proved easier to shoot down. They worked the wing assembly line, installing control surface hinges and aileron mechanisms that would determine whether a pilot could maneuver at 400 miles per hour or lose control during high-speed combat. Her supervisor noted precision and attention to detail in weekly performance reports. Quality control inspectors checked rivet patterns, fuel line connections, and structural integrity before aircraft moved to final assembly stations. Each P-47 carried 364 gallons of internal fuel capacity, supplemented by external drop tanks that extended range enough to escort bombers deep into German territory. The weight distribution required careful calculation. Republic's chief designer, Alexander Kartveli, had engineered the P-47 around the Pratt and Whitney 1800 double Wasp engine, recognizing that raw power and structural strength might prove more valuable than lightweight maneuverability in a war where American pilots would face numerically superior enemies over their own territory. His design philosophy emphasized survivability through redundancy and armored protection rather than performance optimization. The RE 2800 engine represented engineering ambition translated into 1,800 pounds of reciprocating machinery. 18 cylinders arranged in 2 radial rows, each displacing 2,800 cubic inches total, hence the designation. At maximum power, the engine produced 2,400 horsepower, driving a 13-foot diameter propeller that could pull the massive fighter to speeds exceeding 430 miles per hour in level flight. The engine's development had required solving problems that pushed existing engineering knowledge to its limits. Pratt & Whitney's design team, led by Chief Engineer George Meade, had confronted thermal management challenges that threatened to make the design impossible. 18 cylinders firing in sequence generated heat that could melt aluminum components if not properly managed. The solution involved precisely calculated cooling fin geometries, carefully routed baffles that directed airflow across critical surfaces, and metallurgy advances that allowed components to withstand temperatures exceeding 1,000 degrees Fahrenheit during maximum power operation. Each cylinder bore measured 5 3/4 inches in diameter, with pistons travelling 6 inches during each combustion cycle. The mechanical forces involved were extraordinary. At maximum RPM, pistons changed direction from upward to downward travel 43 times per second, experiencing accelerations that would crush human tissue. Connecting rods forged from chrome molybdenum steel transmitted those forces to a crankshaft that had to withstand torsional loads while maintaining rotational balance precise enough to prevent destructive vibration. But the engine's significance extended beyond horsepower ratings. The radial configuration distributed power across 18 separate cylinders, meaning that battle damage affecting 1 or 2 cylinders still left 16 operational. Air-cooled design eliminated vulnerable liquid cooling systems that single bullet hits could disable. Liquid-cooled inline engines, like those powering German Messerschmitts and British Spitfires, required coolant systems where a single punctured line would cause catastrophic overheating within minutes. The RE 2800's air-cooled architecture meant that cooling system damage was virtually impossible. Shoot-away cooling fins and the remaining surface area still provided adequate heat dissipation. The engine's mass, positioned ahead of the cockpit, provided protection that no amount of additional armour could match. 1,800 pounds of steel and aluminium formed a barrier that could stop cannon shells and machine gun rounds that would otherwise penetrate to the pilot. Combat reports documented numerous instances where engine damage had absorbed fire that would have been fatal to the pilot. The radial configuration meant that incoming rounds faced cylinders, crankcase, and accessory sections before reaching the cockpit, each component capable of stopping or deflecting projectiles. Factory test pilots noted that P-47 absorbed punishment that would down lighter fighters, returning to base with battle damage that seemed incompatible with continued flight. One test report, filed by Republic Chief Test Pilot Lowry Brabham, documented a flight test where simulated battle damage was inflicted on a P-47 to determine failure thresholds. The aircraft continued flying with 3 cylinders deliberately disabled, hydraulic pressure reduced to 0, and multiple control cable failures. Brabham's conclusion stated simply that the P-47's redundancy margins exceeded design specifications, suggesting that combat survivability would prove even better than engineering analysis predicted. Foster's paycheck stub showed $1,400 annually for defense work, substantially more than peacetime employment. Her 2 children attended factory childcare while she installed wing components that would face German cannon fire within weeks of installation. Evening shifts worked under floodlights, maintaining 24-hour production schedules that reflected industrial mobilization on scales that made previous American manufacturing capacity seem almost quaint by comparison. The mathematics were straightforward. Aircraft production exceeded combat losses by comfortable margins. Pilot training represented the constraining factor. Each veteran possessed combat experience that training programs couldn't replicate. Knowledge about German tactics and survival techniques learned through missions where mistakes meant death over occupied territory. Engineering decisions that improved pilot survivability directly addressed the bottleneck. Structural strength and armored protection could extend trained pilot operational life by measurable percentages. Republic's final first quarter 1944 production report documented 273 P-47 Sekunde delivered, exceeding contract requirements. But production statistics measured industrial output, not combat effectiveness. The real test would come in European skies, where German fighter pilots were discovering that American Thunderbolts possessed disturbing resistance to damage that should prove fatal. March 7, 1944, 13:20 hours, approaching the Ruhr Valley at 23,000 feet. Lieutenant Johnson's flight of 4 P-47 Sekunde maintained combat spread formation, each aircraft positioned to provide mutual defensive coverage while scanning sectors of sky where German fighters might appear without warning. Radio discipline, limited transmissions to essential navigation updates, and terse warnings that compressed life or death information into single words. The Ruhr Valley stretched below, industrial complexes visible through scattered clouds, factories producing war material that sustained Wehrmacht operations across multiple fronts. American strategic planning assumed that precision bombing combined with fighter superiority could strangle German industrial capacity faster than dispersal and repair efforts could compensate. The assumption required sustained pressure, hundreds of missions that accumulated industrial disruption beyond what German logistics could absorb. Johnson's oxygen mask fogged slightly with each breath, the rubber seal pressing against his face with intimate contact that made the war feel simultaneously distant and immediate. At 23,000 feet, atmospheric pressure was roughly half that at sea level. Without supplemental oxygen, cognitive function degraded within minutes. German fighter pilots faced identical physiological constraints, creating aerial battlefields where human endurance mattered as much as aircraft performance. The first indication of enemy presence came not from visual contact but from radio transmission. Flight leader reported bandits at 2 o'clock high, approximately 4,000 feet above the American formation. Standard Luftwaffe tactics involved altitude advantage, diving attacks that converted potential energy into kinetic velocity, striking with overwhelming speed before climbing back to safety. German pilots had learned that American fighters possessed superior firepower but could be outmaneuvered by aircraft optimized for dogfighting agility. Johnson spotted them, small dark shapes against high clouds, perhaps 8 Focke-Wulf 190s forming up for attack runs. The FW-190 represented Germany's most advanced operational fighter, powered by a BMW radial engine that produced 1,700 horsepower, driving an aircraft that weighed 3,000 pounds less than the P-47. German designers had prioritized roll rate and climb performance, creating a fighter that could outturn most Allied aircraft in horizontal maneuvering. Combat. But aerial combat in 1944 involved more than turning performance. American tactical doctrine emphasized energy management and mutual support, using superior diving speed and firepower concentration to engage on favorable terms. P-47 pilots learned to avoid sustained turning fights, instead using dive and climb tactics that exploited their aircraft's strengths while minimizing exposure to German advantages. The Focke-Wulf's dove, their attack geometry calculated to intercept the American formation with closing speeds exceeding 600 miles per hour. Johnson's flight broke formation, each pilot initiating defensive maneuvers designed to deny German pilots clean firing solutions while maintaining mutual support that would allow counterattacks. The sky became a three-dimensional chess match, played at speeds where mistakes couldn't be corrected. Johnson pulled hard into the attacking fighters, tightening his turn until the G-forces pressed him into his seat with weight that made breathing difficult and narrowed his vision to a tunnel. The P-47's control surfaces responded with authority that belied the aircraft's bulk, ailerons, and elevators moving pistons and cables that translated stick inputs into aerodynamic forces. A Focke-Wulf flashed past, so close Johnson could see the individual panel lines on its fuselage, the black crosses on wings that identified it as enemy. He reversed turn, trying to position behind the German fighter for a firing opportunity, but the FW-190 out-turned him easily, its lighter wing loading allowing tighter radius maneuvers that the massive Thunderbolt couldn't match. Then the second Focke-Wulf appeared in Johnson's peripheral vision, diving from above in a perfect deflection shot that would bring its gun sight across Johnson's flight path at optimal range. No time for evasive maneuver, no time for countermeasures. Just the terrible clarity of recognition that he was about to be hit by a pilot who knew exactly what he was doing. The first cannon rounds struck aft of the cockpit, their impacts transmitted through the airframe as sharp, metallic cracks that felt like physical blows. Johnson instinctively shoved the stick forward, diving away from the attack. But the German pilot anticipated the maneuver, holding his firing run and continuing to pour rounds into the American fighter. 20mm high-explosive shells detonated against aluminium skin, each impact leaving jagged holes surrounded by twisted metal petals. The cumulative effect resembled industrial demolition compressed into seconds. Johnson's instrument panel disintegrated. His radio went silent mid-transmission. Hydraulic fluid began spraying across the inside of his canopy, reducing visibility to abstract patterns of color and motion. The German pilot, Oberleutnant Egon Meyer, commander of Jagdgeschwader II, had accumulated 63 confirmed victories over Allied aircraft. His tactical expertise included precise, deflection shooting and ammunition conservation. Skills developed through 3 years of continuous combat operations. The attack on Johnson's P-47 represented textbook execution, sustained fire from optimal position with the target aircraft unable to evade or counterattack. Meyer held the trigger down, watching his tracer rounds walk across the American fighter's fuselage. His ammunition counters showed rounds remaining dropping rapidly. 150. 100. 75. Standard doctrine called for disengagement after expending half ammunition load, preserving resources for additional engagements or defensive requirements during return to base. But this American fighter continued flying, despite absorbing punishment that should have been catastrophic. The FW-190's 4 MG-151 20mm cannons fired at a combined rate of approximately 240 rounds per minute. Meyer had been firing for nearly 30 seconds. Simple arithmetic suggested Johnson's aircraft had sustained between 100 and 120 cannon strikes, plus an unknown number of 13mm machine gun hits. The P-47 should have disintegrated, should have exploded, should have entered an uncontrollable spin that would end with wreckage scattered across German farmland. Instead, the Thunderbolt continued flying. Its engine still produced power. Its control surfaces still responded to pilot input. The aircraft dove away from the attack, trailing smoke and hydraulic fluid, visibly damaged but fundamentally intact. Meyer broke off his attack, ammunition exhausted, fuel state requiring return to base. His post-flight report would document the engagement with clinical precision, noting the extraordinary durability of the American fighter and recommending revised tactics for engaging P-47 in future combat. Johnson leveled off at 18,000 feet, conducting emergency assessment with the methodical discipline that training had made. Automatic. Engine gauges showed oil pressure dropping but remaining within operational limits. Fuel quantity indicators were shattered, making remaining fuel unknown. Hydraulic pressure had fallen to zero, meaning landing gear and flaps would require manual extension if he made it back to England. The control stick felt sloppy, with delayed response suggesting cable damage or control surface problems. But the aircraft responded. When Johnson moved the stick right, the P-47 rolled right. Forward pressure produced a dive. The fundamental connection between pilot input and aircraft response remained intact, despite damage that had turned the fighter into something resembling a target on a gunnery range. Through his oil-smeared canopy, Johnson could see holes in his wings, jagged punctures that allowed daylight to stream through aluminum skin. The fuselage behind his seat had been shredded, metal panels hanging loose in the slipstream. His back bore impact craters where cannon shells had struck without penetrating. The armor had absorbed hits that would have passed directly through his body. Republic Aviation's design specifications called for armor protection around critical areas. Pilot's seat backed by 3/8-inch hardened steel, engine firewall reinforced with 1/4-inch plating, fuel tanks equipped with self-sealing construction that automatically plugged bullet holes through chemical reaction. These features added weight that compromised performance, but Alexander Kartvel's engineering philosophy prioritized survivability over pure speed or maneuverability. The AT 2800 engine continued running despite visible damage to cooling fins and cylinder heads. Individual cylinders had been struck by cannon fire, their casings cracked, but the engine's 18-cylinder configuration provided redundancy. Power output had degraded perhaps 20%, but 1,400 horsepower remained available from 10 cylinders that hadn't sustained direct hits. The radial engine's distributed architecture meant that catastrophic failure required damage to multiple independent systems, a significantly higher threshold than liquid-cooled inline engines, where single coolant line failure could cause complete power loss within minutes. Johnson faced 200 miles of occupied Europe between his current position and the relative safety of Allied lines. German radar operators would track his progress, vectoring fighters toward a damaged aircraft that couldn't defend itself. Anti-aircraft batteries would engage anything flying at altitudes suggesting Allied origin. The odds of successful return seemed remote, but flying a P-47 that refused to die, despite punishment that defied engineering logic, created a strange form of confidence. He maintained heading toward England, descending gradually to conserve fuel and reduce stress on damaged airframe components. Altitude provided options. If the engine finally quit, he could glide farther. If German fighters appeared, he could dive away at speeds they couldn't match. The P-47's mass, usually a disadvantage in turning combat, became an asset in diving acceleration, where momentum translated directly into velocity. At Luftwaffe operations headquarters in Dalen, Netherlands, intelligence officers compiled engagement reports from returning fighter pilots. The morning's combat had produced claims totaling 8 American fighters destroyed against 3 German aircraft lost. Standard assessment procedures applied verification criteria, requiring gun camera footage or witness confirmation to validate victory claims. But multiple pilots reported engaging P-47 Thunderbolts with concentrated fire that produced no observable results beyond visible damage. The pattern had been developing for months, creating cognitive dissonance among Luftwaffe pilots whose combat experience suggested that sufficient hits on any aircraft would cause destruction. German fighter doctrine emphasized precision gunnery and ammunition conservation, skills developed through years of combat operations. Pilots learned to calculate deflection angles instinctively, positioning their aircraft for optimal firing solutions where brief trigger bursts would place rounds precisely into enemy vital areas. Against RAF Spitfires and early American fighters like the P-38 Lightning, these tactics had proven effective. A well-executed attack producing 10 to 15 hits would typically result in enemy aircraft destruction or mission abort. The mathematical certainty that accumulated damage would exceed structural limits made engagement planning straightforward. Achieve firing position, deliver concentrated burst, observe results, disengage, but P-47 Sekunde violated those assumptions. Pilots reported executing perfect attacks, observing strike patterns that should have been catastrophic, then watching American fighters continue operating as though nothing significant had occurred. The psychological impact was profound. Combat effectiveness depended partly on confidence that tactical execution would produce expected results. When outcomes became unpredictable, despite correct technique, pilot aggressiveness naturally declined. Hauptmann Franz Stiegler, who would later gain recognition for escorting a damaged P-47 to safety rather than destroying it, filed a report that captured growing Luftwaffe frustration with American fighter durability. Engaged P-47 Zoll head-on attack, observed multiple strikes on engine cowling and cockpit area, expected immediate loss of aircraft control or pilot incapacitation. American fighter continued flying, returned fire with 850 caliber machine guns, then disengaged using superior diving speed. This aircraft demonstrates survivability characteristics that render conventional attack methods insufficient for reliable destruction. Stiegler's assessment included detailed observations about P-47 combat behavior that suggested American pilots understood their aircraft's survivability advantages and exploited them tactically. Rather than avoiding combat when damaged, P-47 pilots often continued engaging, using their aircraft's armament and diving speed to remain threatening even after sustaining hits that would force other fighters to disengage. The tactical implication was clear. Fighting P-47 Sekunde required accepting that even successful attacks might not produce aircraft destruction. The assessment circulated through Luftwaffe technical intelligence offices, where engineers studied captured P-47 components and damage reports to understand what made the American fighter so difficult to down. Their analysis revealed design philosophy that contrasted sharply with German approaches. Where German fighters optimized for performance through weight reduction and aerodynamic refinement, the P-47 emphasized structural strength and system redundancy. German technical reports documented specific characteristics that contributed to P-47 survivability. The radial engine's 18 cylinders provided multiple independent power sources. Hydraulic systems featured backup components that maintained partial function even after battle damage. Control cables were routed with redundancy, allowing continued aircraft control despite hits that severed individual connections. Armor protection surrounded critical areas, not comprehensively, but strategically positioned where combat experience indicated vulnerability. One particularly detailed analysis, prepared by Luftwaffe technical officer Major Erich Sommer, compared P-47 design philosophy with German fighter development. Sommer noted that German engineers had consistently prioritized performance parameters, climbing rate, turn radius, maximum speed, accepting reduced structural margins to achieve superior maneuverability. The approach reflected Luftwaffe doctrine emphasizing pilot skill and tactical flexibility over aircraft durability. German engineers noted with professional respect that Republic Aviation had created an aircraft that accepted certain performance limitations in exchange for battlefield survivability that exceeded comparable fighters by measurable margins. The trade-offs were deliberate and mathematically justified. A P-47 that survived to return home could fly another mission. A higher performance fighter that was easier to shoot down removed both aircraft and irreplaceable trained pilot from operational availability. Johnson crossed the English Channel at 6,000 feet, low enough that German radar lost track of his damaged fighter among ground clutter. RAF coastal stations picked up his radio transmission requesting emergency landing clearance at Manston, the forward airfield equipped for handling battle-damaged aircraft. Tower operators cleared all other traffic, deploying crash crews to positions along the runway, where foam equipment could respond if Johnson's landing attempt resulted in fire or structural failure. The P-47 approached the runway with no flaps, no landing gear position indicators, and minimal control response. Johnson had manually cranked the landing gear down using emergency procedures, but without hydraulic confirmation, he couldn't verify whether the gear had locked in position. The landing would either work or it wouldn't. No amount of preparation could change odds that depended on mechanical components that might have been damaged beyond function. Touchdown came hard, the P-47's weight slamming onto the runway with impact that would have collapsed compromised landing gear, but the gear held. The aircraft rolled straight despite damaged control surfaces, bleeding speed until Johnson could apply brakes that still functioned mechanically even without hydraulic boost. The fighter stopped 3/4 down the runway, trailing smoke from overheated brake assemblies, but intact and survivable. Silently, counting damage that seemed incompatible with the flight they had just witnessed. Over 200 individual bullet and cannon strikes, 3 cylinders with visible battle damage, hydraulic lines severed in multiple locations, control cables frayed where fragments had struck, fuselage panels shredded. Yet every critical system had maintained sufficient function for the pilot to return home. Technical Sergeant Frank O'Brien, whose maintenance experience included repairing fighters since the North African campaign, walked the length of Johnson's P-47 with increasing astonishment. He had seen battle-damaged aircraft before, had patched holes, and replaced components on dozens of fighters that had survived German attacks. But this damage exceeded anything in his experience. This wasn't a fighter that got lucky. This was engineering that had anticipated catastrophic battle damage and designed around it with precision that bordered on prescient. O'Brien's preliminary damage assessment, documented on standard maintenance forms that would be forwarded to Republic Aviation and Army Air Forces engineering offices, catalogued destruction that read like battlefield casualty report. Engine cowling panels, 17 separator penetrations, including 3 complete perforations of cooling baffles. Right wing upper surface, 32 bullet holes, ranging from 7.9mm machine gun strikes to 20mm cannon impacts. Left wing, 28 penetrations with 2 spar members showing impact damage but maintaining structural integrity. Fuselage damage was most extensive. The area aft of the cockpit had sustained concentrated fire that destroyed radio equipment, oxygen system components, and hydraulic reservoirs. Yet critical flight control cables, routed through this section, remained intact. Republic's engineering specifications called for control cable redundancy and protective routing that positioned cables where structural members would provide shielding against likely damage vectors. The design had worked exactly as intended. O'Brien's crew began damage assessment procedures that would determine whether the aircraft could be repaired at field level or required depot maintenance. Each damaged component was evaluated against technical manuals that specified repair criteria and replacement procedures. Engine cylinders with visible damage would require removal and inspection to determine if internal components had sustained collateral harm. Hydraulic system repairs needed pressure testing to verify integrity after line replacement. Control surfaces required rigging checks to ensure proper aerodynamic function. The assessment process revealed Republic Aviation's maintenance-focused design philosophy. Components were accessible through panels that could be removed with standard tools. Damaged sections could be cut away and replaced without affecting adjacent structures. Standardized parts meant that replacement components were available from supply chains that maintained inventory across European theatre bases. The P-47 had been designed not just to survive combat damage, but to be repaired quickly using available resources and typical maintenance crew skills. Sergeant Thomas Malloy, a hydraulic systems specialist, traced the damage through fluid lines that had been completely severed by cannon fire. The P-47's hydraulic system featured redundant pressure sources and isolated circuits that prevented total system failure even when primary components were destroyed. Johnson had lost hydraulic pressure, but manual backup systems had allowed gear extension and basic flight control. The engineering had anticipated exactly this failure mode, providing alternatives that maintained minimum functionality. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Johnson's post-flight debriefing lasted 2 hours, during which intelligence officers documented every phase of the engagement. His testimony provided data points that would inform tactical doctrine and mechanical improvements, but the broader lesson transcended individual combat report. The P-47 had demonstrated survivability that validated Republic Aviation's design philosophy and challenged assumptions about optimal fighter characteristics. Colonel Zemke reviewed Johnson's gun camera footage and damage assessment reports, noting patterns that confirmed observations from other combat missions. P-47 were surviving encounters that would destroy lighter fighters. The survivability translated directly into operational effectiveness. Pilots who returned from missions could fly again, experience accumulated, tactical knowledge increased. The combination of human expertise and aircraft durability created compounding advantages that pure performance specifications couldn't capture. Zemke's tactical analysis, distributed to fighter group commanders across the 8th Air Force, emphasized how P-47 characteristics enabled aggressive employment that would be reckless with less survivable aircraft. The fighter's ability to absorb battle damage meant pilots could press attacks longer, accept greater risks during bomber escort missions, and conduct low-altitude strafing operations where anti-aircraft fire created hazardous environments. Each tactical advantage multiplied overall combat effectiveness. The 56th Fighter Group's mission statistics illustrated the broader pattern. Through March 1944, the group had lost 32 P-47 to all causes, combat and operational. During the same period, they had flown over 3,000 sorties, engaged in numerous sustained combat actions, and claimed 116 German aircraft destroyed. The loss rate of approximately 1% per sortie was significantly lower than early warfighter operations that had seen attrition rates exceeding 5% during intensive combat periods. More significantly, pilot casualty rates remained lower than aircraft loss rates. Some pilots survived aircraft loss through successful bailouts over friendly territory. Others landed damaged aircraft that were written off as beyond economical repair but preserved the pilot's life and experience. The mathematical relationship between pilot survival and long-term squadron effectiveness couldn't be overstated. A squadron that maintained experienced pilot corps could execute complex tactics, mentor replacement pilots effectively, and sustain high operational tempo that inexperienced units couldn't match. Zemke initiated a comprehensive study of P-47 combat effectiveness that would inform aircraft procurement and tactical doctrine development. The study examined not just kill ratios and mission success rates, but survivability metrics that measured how aircraft characteristics influenced pilot preservation. The analysis revealed that P-47 pilots were completing combat tours at higher rates than pilots flying comparable missions in other fighter types, even accounting for differences in operational deployment and tactical employment. The strategic implications extended beyond individual squadron performance. American air strategy in Europe depended on achieving air superiority that would enable strategic bombing operations and support eventual ground invasion. Air superiority required not just producing more fighters than Germany, but maintaining experienced pilot cadres that could execute sophisticated tactics against skilled opponents. Aircraft survivability directly enabled that strategic objective by preserving human capital that couldn't be rapidly replaced. Within the Luftwaffe command structure, Johnson's survival became part of accumulating evidence that American fighter operations had achieved qualitative superiority that numerical analysis couldn't fully explain. German pilots still possessed skill advantages in many cases. German fighters still demonstrated superior maneuverability, but American aircraft could absorb punishment and continue fighting, a characteristic that altered combat mathematics in ways that made individual engagement victories less meaningful than sustained operational capability. Oberleutnant Egon Meyer, whose attack on Johnson had been executed with textbook precision, found himself confronting tactical problem without clear solution. Standard engagement methods that had proven effective against Spitfires and early American fighters produced insufficient results against P-47 Sekunde. The American fighters' combination of firepower, speed, and survivability created engagement conditions where even successful attacks failed to remove enemy aircraft from combat. Meyer had commanded fighter units since 1940, accumulating combat experience across multiple theaters and against various Allied aircraft types. His tactical expertise was recognized throughout the Luftwaffe, making him qualified to assess new threats and develop counter-tactics. But the P-47 presented challenges that conventional solutions couldn't address. The aircraft's survivability margins exceeded anything Meyer had encountered in 4 years of continuous combat operations. His tactical assessment, circulated through Jagdgeschwader 2 and eventually distributed to other fighter units, outlined specific problems P-47 Sekunde created for German tactics. First, the aircraft's diving speed made disengagement virtually impossible once American pilots chose to break off combat. German fighters that had achieved advantageous position would watch P-47 Sekunde simply dive away at speeds approaching 500 miles per hour, velocities that German aircraft couldn't match without risking structural failure. Second, the P-47's 850 caliber machine guns produced concentrated firepower that made head-on attacks hazardous. German fighters traditionally used head-on attacks to engage bomber formations, accepting brief exposure to defensive fire in exchange for optimal shooting geometry. Against P-47 Sekunde, head-on approaches meant facing combined firepower of 8 heavy machine guns that could destroy a fighter with just a few hits. The risk-reward calculation made head-on attacks tactically questionable. Third, and most frustrating, the aircraft's survivability meant that even successful attacks often failed to produce aircraft destruction. Meyer had personally observed P-47 Sekunde absorbing damage that would have downed any German fighter, yet continuing to operate effectively. The psychological impact on German pilots was significant. Combat effectiveness depended partly on confidence that proper tactical execution would produce expected results. When outcomes became unpredictable, despite correct technique, pilot morale and aggressiveness suffered. Meyer's professional assessment, documented in Luftwaffe tactical bulletins, recommended avoiding sustained engagement with P-47 formations, unless German fighters possessed overwhelming numerical or positional advantage. The recommendation reflected acknowledgement that American industrial capacity was producing not just large numbers of fighters, but fighters designed with battlefield realities that German engineering had not fully anticipated. The tactical bulletin included specific engagement recommendations that represented significant departure from standard doctrine. Concentrate attacks on engine compartment using armor-piercing ammunition, multiple fighter coordination essential, requiring 3 to 4 aircraft attacking single target to ensure sufficient damage accumulation. Avoid prolonged engagement, German fighters should execute single attack pass, then disengage before P-47. Sekunde can respond with superior diving speed. If possible, avoid combat entirely, preserving German fighter strength for bomber interception, where tactical necessity justifies accepting casualties. The final recommendation was particularly telling. It acknowledged that P-47 Sekunde had fundamentally altered tactical calculations, forcing German fighters into defensive posture, where engagement occurred only when mission requirements made combat unavoidable. For a Luftwaffe that had dominated European skies through 1942, the psychological shift was profound. The broader strategic implications became visible through attrition statistics that measured not just aircraft lost, but pilots preserved through enhanced survivability. American fighter pilot casualty rates in early 1944 showed measurable improvement compared to previous years, despite increasing combat intensity and deeper penetration into German-controlled airspace. The improvement correlated directly with P-47 deployment and the aircraft's demonstrated ability to bring pilots home even after sustaining catastrophic damage. March through June 1944, Republic aviation production facilities expanded operations to meet demand that exceeded original contract requirements. The success of P-47 in combat had created requests for additional aircraft from every theatre where American forces operated. Factory floors ran 3 shifts, producing fighters at rates that consumed raw materials faster than supply chains could deliver aluminium, steel, and high-grade aviation alloys. Margaret Foster's work crew installed wing components on aircraft that would deploy to Pacific theatres, where P-47 were proving equally effective against Japanese fighters. The design characteristics that provided survivability over Europe, rugged construction, powerful engine, heavy armament, translated directly into advantages against opponents who relied on lightweight maneuverability and pilot skill. American fighters could absorb damage and continue fighting, a tactical advantage that compounded through sustained operations. Technical innovations implemented during production included improved turbo supercharger systems that enhanced high-altitude performance, upgraded ammunition capacity that increased combat persistence, and refined armor configurations that protected critical systems without excessive weight penalties. Each improvement reflected lessons learned from combat operations, mechanical evolution, guided by battlefield data rather than theoretical performance optimization. Republic's engineering staff analyzed battle damage reports from European and Pacific theaters, identifying patterns that revealed both strengths and vulnerabilities in existing designs. The Wright 2800 engine demonstrated remarkable durability, but cooling system components showed susceptibility to damage that could degrade performance during extended combat. Fuel system self-sealing mechanisms worked effectively against rifle-caliber ammunition, but struggled with larger cannon rounds that created damage beyond chemical sealant capacity. The analysis produced running modifications implemented across production runs, incremental improvements that increased survivability margins without requiring complete redesign. Cooling system redundancy increased. Fuel tank construction evolved to handle larger punctures. Control system routing incorporated additional backup pathways. Each change added modest weight and complexity, but the cumulative effect measurably improved aircraft capability to sustain battle damage and return pilots home. By summer 1944, P-47 production exceeded 400 aircraft per month, with quality control standards that maintained structural integrity and system reliability despite accelerated manufacturing pace. Factory test pilots noted consistent performance characteristics across production aircraft, indicating that rapid expansion had not compromised manufacturing precision. The industrial mobilization that had seemed impossible in 1941 had become routine capability by mid-war, producing military hardware at scales that made pre-war planning assumptions appear conservative. Lieutenant Robert Johnson returned to operational status within 2 weeks of his March engagement, flying the same repaired P-47 that had absorbed over 200 hits. Maintenance crews had replaced damaged components, patched fuselage panels, and verified system functionality through comprehensive test procedures. The aircraft's structural integrity remained sound despite extensive battle damage, validating Republic's engineering approach that designed for combat survival rather than pristine performance optimization. Johnson's subsequent missions added to growing body of evidence that P-47 durability provided tactical advantages beyond simple survivability. Pilots confident in their aircraft's ability to absorb punishment engaged more aggressively, pressing attacks where lighter fighters might have disengaged. The psychological impact of flying nearly indestructible fighters translated into operational tempo that German forces struggled to counter. German technical intelligence continued analyzing P-47 characteristics, seeking vulnerabilities that could be exploited through revised tactics or specialized weapons. Luftwaffe armament officers developed proposals for heavier cannon installations and concentrated fire doctrine designed specifically for engaging the American fighter. But implementing new tactics required time, resources, and training infrastructure that Germany's deteriorating strategic position couldn't support. The asymmetry became increasingly apparent through 1944. American industrial capacity produced fighters faster than combat operations consumed them, creating numerical superiority that compounded qualitative advantages. German aircraft production remained substantial, but replacement pilot training lagged behind aircraft availability, creating situations where modern fighters sat idle for lack of qualified pilots. Meanwhile, American pilots accumulated combat experience in aircraft that brought them home even after encounters that should have been fatal. June 6, 1944, the Allied invasion of Normandy proceeded under air superiority umbrella that P-47 Sekunde had helped establish through months of sustained operations over occupied Europe. Fighter squadrons flew close air support missions, providing direct assistance to ground forces that marked fundamental shift in tactical aviation employment. The P-47's rugged construction proved ideally suited for low-altitude operations, where anti-aircraft fire and ground obstacles created hostile environment that lighter fighters couldn't survive. Ground attack missions exposed P-47 Sekunde to damage patterns different from air-to-air combat. Small arms fire, light anti-aircraft guns, and debris from exploding targets created cumulative damage that tested aircraft survivability in new ways. The radial engine's distributed cylinder arrangement again proved advantageous, allowing continued operation despite multiple hits that would disable liquid-cooled engines. Pilots reported successfully completing missions after sustaining ground fire that perforated wings, damaged landing gear, and destroyed cockpit instruments. Technical Sergeant O'Brien's maintenance crews developed rapid repair procedures that returned battle-damaged aircraft to operational status within hours rather than days. The P-47's straightforward construction facilitated field repairs, with accessible components and standardized parts that maintenance personnel could replace without specialized tools or extensive training. Combat units maintained higher aircraft availability rates than comparable fighter groups operating more complex aircraft designs. The operational tempo sustained through summer 1944 demonstrated how survivability translated into strategic capability. American fighter groups flew multiple missions daily, maintaining continuous pressure on German forces that couldn't be replicated with less durable aircraft. Individual pilot effectiveness increased as experience accumulated without corresponding increase in casualty rates. The mathematical relationship between survivability and combat power produced multiplicative effects that pure production numbers couldn't capture. By autumn 1944, Luftwaffe fighter strength had degraded to levels that made effective defense of German airspace increasingly difficult. American P-47 Sekunde and P-51 Sekunde ranged across Germany with minimal opposition, attacking transportation networks, industrial facilities, and remaining Luftwaffe airfields with relative impunity. The air superiority that had seemed uncertain in early 1943 had become established fact, enabled partly by aircraft design decisions that prioritized pilot survival over performance optimization. Lieutenant Johnson completed his combat tour in October 1944, having accumulated 27 confirmed aerial victories and surviving numerous encounters where his P-47's durability had made the difference between survival and casualty. His post-war testimony provided historical perspective on how aircraft characteristics influenced individual survival and broader tactical outcomes. The P-47 brought me home, he stated during interviews years later, not once but dozens of times. Every pilot who flew that aircraft owed their life to engineers who understood that the war wasn't won by the fastest fighter, but by the one that kept flying after being hit. German archives captured in the war's final months revealed the full extent of Luftwaffe concern about P-47 survivability. Intelligence assessments documented that American fighter durability had forced tactical revisions, reduced German pilot aggressiveness and contributed to unsustainable attrition rates among experienced Luftwaffe aviators. The psychological impact of engaging opponents who seemed nearly invulnerable created operational effects beyond pure kill ratios or mission success statistics. One captured document, a tactical bulletin distributed to Luftwaffe fighter units in March 1944, contained remarkable acknowledgement. Engaging P-47 Thunderbolts requires acceptance that multiple hits producing visible damage may not result in aircraft destruction. Pilots should concentrate fire on engine compartment and continue engagement until either enemy aircraft shows signs of complete incapacitation or ammunition exhaustion requires disengagement. The American fighter demonstrates survivability characteristics that exceed standard engagement assumptions. The technical language barely concealed deeper frustration. German fighter pilots, among the most skilled aviators of the war, found themselves unable to reliably destroy enemy aircraft even when executing textbook attacks. The mathematical certainty that sufficient hits would down any aircraft was colliding with engineering reality that had designed around that very assumption. Republic Aviation's engineers had anticipated exactly the combat conditions that German pilots would create, then built an aircraft that could survive those conditions. The story of Johnson's March 7th engagement circulated through both American and German aviation communities, achieving almost mythical status that subsequent investigations would verify through combat reports and damage documentation. The incident represented not unique occurrence, but exemplary case of broader pattern. P-47 Sekunde routinely absorbed catastrophic damage and continued flying, bringing pilots home who shared their survival stories and flew subsequent missions. Final wartime statistics documented P-47 combat record with precision that validated engineering decisions made years earlier during design phase. Over 15,000 P-47 Sekunde entered service across all theaters. The type achieved favorable kill-to-loss ratios against all opponents, but more significantly, demonstrated lowest pilot casualty rate among American frontline fighters. Survivability translated directly into preserved human capital, allowing experienced pilots to accumulate mission totals that created compounding tactical advantages. Post-war analysis by United States Strategic Bombing Survey examined how fighter characteristics influenced air superiority campaigns. The assessment concluded that aircraft survivability had proven equally important as performance characteristics in determining operational effectiveness. Fighters that could absorb battle damage and return pilots home maintained higher squadron experience levels, better tactical execution, and greater sustained combat capability than higher performance aircraft with inferior survivability. Alexander Kartfelis's design philosophy, controversial during development when critics questioned accepting performance penalties for durability, had been vindicated by battlefield results that demonstrated engineering wisdom exceeded conventional assumptions. The P-47 represented successful integration of multiple design priorities, sufficient performance for combat effectiveness, overwhelming firepower that compensated for maneuverability limitations, and survivability that preserved irreplaceable human expertise. The broader lessons transcended specific technical details about radial engines and structural design. Military effectiveness resulted from complex interaction between hardware capabilities, tactical doctrine, industrial capacity, and human factors. Optimizing single characteristics at expense of system-level performance produced weapons that performed well in testing but failed under operational conditions that designers hadn't fully anticipated. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.